All right, so welcome back to section 3, naive Bayes. Where we left off on Tuesday, we talked a little bit about why logistic regression might not be the best model for a particular classification problem. Again, when classes are well separated, when there's a big distinction or gap between the zeros and ones, logistic regression is pretty unstable. If we have a small sample size, other methods do tend to perform better, but most importantly, logistic regression is limited in terms of the predictions that we can make. We can only predict for 2 classes, certainly can't handle 3 classes or more. So instead of logistic regression, we might build a model or build a classifier using Bayes' theorem. So Bayes' theorem is a way for us to get conditional probabilities based on some prior assumptions. So for each of our new inputs that we want to predict for, say x, what we'll do is find a posterior probability that given an input x, we are in class K. We'll find that based on some weighted combination of the prior probabilities. We call those pi. And then the density function. So here the density function is the conditional distribution of the input given class membership. So for each observation, we'll calculate this posterior distribution. We'll predict class K such that the posterior distribution is maximized. Now this is a general Bayes classifier. There are lots of different versions of Bayes classifiers. The most common is naive Bayes. Naive Bayes is naive, because of some assumptions that it makes and how it is calculating those prior probabilities. So we looked at an example on Tuesday with the Fisher data set. We walked through building the model using the train function, and we also talked a little bit about some metrics for evaluating this model. Specifically, how can we use Cohen's kappa to evaluate a classifier, and what does that kappa actually represent? Kappa represents the improvement over random chance classification. Now, once we have built this model, we might want to take a look at what is contained in the model object in R in particular to see what we can learn about how well the model has been fit. So if we look at just the names of all of the different values or all of the different arrays or objects that are stored within this model in R, you can see we've got a lot of choices. We've got the method, so we're storing what method we're using. The model info, this is going to be the model formula. We're storing the results of the model. Then we're storing some metrics, then a bunch of other information as well. If we want to take a look at any of these objects or any of these arrays within the model, we can just use R's $ notation. So writing model $ levels will extract the levels from our model. Here the levels are actually the classification classes that we're predicting. So for the iris data set, the levels are Setosa, versicolor, and virginica. We want to also keep track of whether or not these are what are called ordinal variables, whether or not the classification classes have some natural ordering or sequencing. They are not ordered. This attribute is false. All right, so we'll skip the good kappa and we'll take a deeper dive into some of the characteristics of this model. So anytime we want to look at the specifics of the final model that train is choosing for us, we'll look at the model $ final model. So here we're using naive Bayes. This is the call or the formula that we're using within that train function. So we're defining our x's, these are input variables, our y's. These are all set up when we write that model formula. So in the background, train is creating a set of x variables and a set of y's for the outputs. Laplace, this is one of the tuning parameters for naive Bayes. And then use kernel equals false. That was the model that was shown to have the best accuracy when we looked at a summary of this model. So as we scroll down, we see some information here. First thing I want to point out are the a priori probabilities. These are the priors. These are the pi's that we're using to calculate those posterior probabilities. You might notice that we're using even probabilities here. So setosa has a 1/3 probability, versicolor has a 1/3 probability, virginica has a 1/3 probability. There's two possible explanations for this. One being that we're assuming even probabilities for all of the classes as sort of a flat or uninformative prior. However, what is actually happening is that we're taking the class frequencies out of our y's, out of our observed data. So we're actually just taking how often each of these classes are occurring in the data. In this case, there were 50 setosas, 50 versicolors, and 50 virginicas. So that's where we get the 1/3, 1/3, 1/3. We also can get some summary tables. Here we're looking at summary information for both sepal length and sepal width, specifically the mean and standard deviation for each of the 3 varieties. Now remember, when this used kernel equals false, our classifier is assuming that these numerical x inputs are following a normal distribution or are following a bell-shaped curve. In order to fully parameterize or fully describe that bell-shaped distribution or that Gaussian distribution, we do need the mean and standard deviation. So that's why these particular summary statistics are the ones that are being returned. Let's say we want to look at the model prediction. So something that looks like it might be promising in this model names is this pred item. However, if we look at the pred object within the model, we get back a null. Those predictions are empty. It turns out that instead, we need to apply the predict function to actually do those predictions. So if we use the predict function on our model, what will happen is that R will make predictions on the data that was used to build the model. So these are the predictions for the original data. Now, interestingly enough, in the iris data set, the original observations are sorted. So all of the setosas are written first, all of the versicolors come next, all of the virginicas come next. So we're seeing, just looking at these predictions, that we're classifying the setosa irises pretty well. The virginica and versicolor, however, there is a lot of overlap, so we might not be classifying those as well. To take a better look at the accuracy, we can construct what's called a confusion matrix. So a confusion matrix is a table that gives us the predicted values compared to the actual values, or in this case, the reference values in the data set. In order to create this confusion matrix, I'm first going to take those predictions from my model, add them to the iris data set using a mutate command. So iris $NB prediction, these are my naive Bayes predictions. So that goes into the confusion matrix as my data. My reference argument is iris $species. What we want to see with this confusion matrix is lots of numbers on the diagonal. We want to see very high counts on those diagonals. Those indicate correct classifications. We want to see lower counts on the off diagonals. Those are incorrect classifications. So for example, for the actual setosas, 49 out of them we've correctly classified using this model as true setosa irises. One of the true setosas was classified or predicted to be versicolor. Versicolor and virginica we're not doing as well with. So the good news is we're not classifying any of the true versicolors or virginicas as setosas. Those are all zeros. However, we're having a much harder time distinguishing here and here. We also get an overall accuracy rate, a 95% confidence interval for the accuracy rate. We get a no information rate. This is the same as that expected accuracy from previously. So this is how we would expect to do if we were just assigning all observations to a class at random. And then our p-value, is our accuracy significantly better than this no information rate? Absolutely. We've hit the point where R stops calculating the p-value, so this is as small as we're going to see in practice. We also get a kappa. We get something known as a McNemar's test result. McNemar's test is used to compare 2x2 contingency tables. So here there's no p-value recorded for McNemar's test because we have a 3x3 table. And then we also have some statistics by class. So for each class of iris, we have sensitivity, specificity, positive predicted values, negative predicted values, prevalence, detection rate, and so on. I want to talk a little bit about what we're seeing in this statistics by class table. So, if you'd like to know how all of these are calculated, in the documentation for CARET, there's a set of formulas for how we're getting sensitivity, specificity, prevalence, PPV, NPV, and so on. So all the way down. However, these are all metrics that are defined against a 2x2 class. So what's happening is when there are 3 or more classes, the confusion matrix is going to return one versus all results. So instead of using this confusion matrix to evaluate our predictions on Setosa, we'll construct a new one that is 2x2, Setosa versus everything else. So we would have 49 here. Our everything else category is going to have the number of all of the others that we've classified correctly. So 37 plus 31. Then we'll collapse down these other misclassifications into that table as well. So that's how we're doing these statistics by class. We're doing one class against all of the other options. If we want to take a look at the model accuracy, one thing that we might want to do is plot the predictions. So let me walk you through this plotting code. So again, we're taking the iris data set. I'm using a mutate function to create a new variable called NB_correct, or naive Bayes correct. So if my prediction is exactly equal to the species, this will take on true. Otherwise, or else, it will take on false. So we'll keep track of whether or not we've predicted correctly. I'll plot my sepal length against the original sepal width, so my 2 input variables. I'm going to add an ellipse here around each of the species so we can kind of visualize where we might naturally classify. The geometry here says polygon, so that's going to shade in my ellipse. Alpha equals 0.2 is going to make it translucent. And then finally, I'm going to add some points on top of that ellipse. I'm going to change the color based on whether or not they were correct classifications, and the plot character, or PCH, based on the species. So here we go, and here's the information that we're getting from this. So the Setosas generally are in this region. The versicolors are generally in this green region. The Virginicas are in this blue region. Those ellipses are definitely overlapping. Points that are the coral red color are false. So this is where we're misclassifying. So we're misclassifying here, here, and then we're misclassifying a bunch where these ellipses overlap. True, that's where we're correctly classifying. So these teal points are the ones where we are accurate in our predictions. The plotting character, the shape of the plot, changes depending on the actual species. So you can see a lot of coral squares. These are the misclassified Virginica irises. The coral triangles are the misclassified versicolor irises. Now, one thing that we have sort of danced around is how we're deciding what data to put in. So in machine learning, we're especially concerned about a problem known as overfitting. Essentially, we want a model that strikes a good balance between being too simple or underfit, or overfit, just too good to be true. The problem with overfitting is that we end up in a situation where we perform really, really well on the data that we've used, but we perform less well with new data or new observations. We've essentially tried to make too much of a pattern or of the data we have at hand. So what we do when we fit our machine learning model is employ a validation technique. So validation is the process we use to obtain an unbiased estimate of the error that's associated with a machine learning algorithm. So we want to make sure that we are avoiding that overfitting problem. Again, those machine learning algorithms are built or optimized to minimize prediction error on the input data set. If we use all of the data we have available for that input data set, we've got no way to measure how well we would do on a new set of observations. So we employ a validation strategy. There's two common ones that are used and that you've likely encountered before. The first is the holdout method. So in the holdout method, we keep back or remove a portion of our data to test the model on. So we would use this training set to build our model, estimate the parameters, and then use this testing data set of held back observations to get an idea of how we're actually doing, so how our model is performing. The percentages that we're using here for this training and testing data set, there's really no right answer as to what is the best amount of data to hold back. Your choice should depend on the amount of data that is available and how certain you are or how much you want to avoid that overfitting problem. In practice, you commonly see things like a 50-50 training test split, 75-25, 70-30, 80-20. This split always refers to the training percentage and then the test percentage. Generally, that test percentage is going to be lower or at most 50% of the data. Another strategy that we might use is what's called k-fold cross-validation. So picture repeating this testing training assignment k times, and then we aggregate the results. Building a model using k-fold cross-validation takes significantly longer because we're fitting the model not just one time on one training data set, but we're fitting it k times on k training data sets. We'll come back to k-fold cross-validation and how to implement it a little bit later once we have some more classification algorithms under our belt. But for now, I want to take a look at how you would implement the holdout method. So in Caret, we have a nice function called create data partition. And what this does for us is create that testing and training split in a way that is what's called balanced. So here is how this function works. First thing I want to highlight is that I've actually set a seed in this document. Usually I will set my seed to be 366. In general, I pick the course number because it's an easy number to remember. What that's going to do is make sure that the randomization is exactly the same every time I execute this code. So if you want your results to be consistent, make sure you're setting a seed number somewhere at the beginning of your assignments or your work. So I'm going to create a data partition, and I'm going to create a data partition using the species variable from the iris data set as my target variable. This is the output that I want to classify as. I'm going to set p to be equal to 0.8. This p is the size of my training data set. So my training data set is going to contain 80% of the observations. I don't want this to be returned in list format. I want this to be returned in data frame format. So list is equal to false and times is just 1. I'm just going to create one testing training split. So now what I've done is create a vector index called train index. And what this actually contains isn't my training data, but rather row numbers that I can pull out of my original data set to create my training data. So create data partition, again, isn't actually creating the split, it's just giving you an index of row numbers. So our train index says to take row 1, row 2, row 3, row 5, row 7, and row 8 and put those in the training data. With that head function, we're only looking at the first 6 observations. This will go on to contain 120 or 80% of the rows in the data. So using row column notation, I'm going to stick the rows with the training index into a new data set called iris train. Here in R, this bracket notation indicates the rows to take. The columns are left blank, so that means bring all of the columns over. Iris minus train index says to take everything that is not in that train index, all of those rows that were left out of the training data set, and put them into the testing data set. So that's what we'll use for our model validation. What is happening when we're creating those balanced splits is that we're setting up our training and testing data to have the same proportion of classes. So in other words, we're equally dividing those Setosa classes between the training and testing data, equally dividing the versicolor between training and testing, and equally dividing Virginica between the training and testing data. If we don't necessarily care about having that balance in our testing and training data, we can use just simple random sampling. So here what I've done is create a second training index. This second training index, is going to take as samples values that are integers going from row to the number of rows in the iris data set. The size is going to be 0.8, so that's the proportion I want in my training set, times the number of rows in the iris data set. And then here I'm applying a floor function just in case we ended up in a situation where this was not an integer value. Taking a floor says to drop that decimal and just take the integer part of the number. So we might do this if we have, say, non-integer values for this proportion times our training data. So if we take a look at this second train index, this is the unbalanced training index. We're taking row 117, row 140, row 24, row 9. Since we're doing simple random sampling, these indices are going to be out of order, and that's okay. We'll build our unbalanced training data, our unbalanced testing data, and here you can see that we have fairly different class frequencies within these. So we're building our model with proportionally fewer versicolors than Setosa and Virginica. If we're especially concerned about how well we're predicting for a particular class, we might use a balanced split. Whereas if we're not as concerned about it, or if we have a lot of information regardless, maybe taking a balanced split of the data isn't going to help us that much. So let's apply that naive Bayes classifier to the iris dataset, and we're going to do this using the balanced testing training data. So instead of feeding the full data in, we're just using that training data. So this is 80% of our original observations. Our accuracy has gone down a little bit. Kappa looks like it's gone down a little bit as well. Accuracy and kappa are greater when we are not using the kernel estimation method, so that will be our final selected model. We haven't asked to fiddle with or manipulate these other tuning parameters, Laplace equals 0, adjust equals 1, so we'll just leave those at their defaults. To see those predictions then on the testing data set, we'll use the predict function. The new input here is providing our new data. So we want to make predictions not on the training data, but on the testing data. So we'll feed in our new data to be the testing data. We can see again the predictions. We'd like to know how we're doing on this new data. So same sort of plot with the ellipses. However, I've generated this just with the new testing data. So this is only 20% of our observations. Again, we're doing pretty well with the Setosas. We're still having some trouble distinguishing between versicolor and Virginica irises. Now, let's talk again about what makes this a naive Bayesian approach. So naive Bayes assumes that each of the input variables is independent, and that is usually not the case. even with these limited set of observations in our testing data set, there's a slight downward association between sepal width and sepal length. Plants with longer stems tend to have thinner stems and vice versa. So if there's correlation between our input variables, naive Bayes might not work as well. The other thing that makes this naive is that we're assigning those prior probabilities not based on any additional knowledge, but just based on the original class frequencies or the class proportions. So let's take a look at applying naive Bayes on another data set. So this is the default data set that we saw with logistic regression. We have whether or not customers defaulted on their credit card, whether they're a full-time student, we have their credit card balance, and the customer's income. Looking at this data set, there's one definite difference between the credit card data set or the default data set and the iris, namely the size of this data set. The default data set is much larger. We have 10,000 observations. We also don't have a very clear distinction. It's difficult to look at this and see where we might draw the line between default versus not default. Here we're looking at just income and balance on a two-dimensional plot. So let's build a testing and training data set and use the model to predict whether or not customers default. So we are using a 75-25 training testing split. So 75% of our observations will be used to build the model. 25% will be used to evaluate the model. Here, again, I've just copied that same code as before with the floor, just in case. We'll set up our train data set using the train index. We'll set up our default data set by we'll set up our test data set by removing the train index, and then we'll build our model. Again, just so we can visualize this, I've chosen to use only two input variables, only income and balance. So overall, our accuracy for this model is pretty strong, looks pretty good. Our kappa, much less strong. That has to do with the frequencies in the data. So there are so few observations where we're actually even seeing customers default on their credit card. So if I predicted that nobody would default, I would still have a pretty good accuracy rate. And that's why compared to the overall accuracy, the kappa is much lower. Here it looks like kernel density estimation did perform a little bit better. We have some slight improvement on the accuracy, so we're using that kernel method. In other words, we're not assuming a normal distribution on income and credit card balance. Looking at our default model, the prior probabilities here reflect that we're using those class frequencies. So in the, I like to scroll. In the training data, we have about 97% of our customers not defaulting, only about 3% are, so that's where we're getting our pies. Here we're using kernel density estimation, so the statistics we need to implement that are just a little bit different. For the income, no, income predicting to yes default. Here are some summary statistics on the X's. On the Y's, balance predicting to no, balance predicting to yes. And again, we'll talk more about what kernel density estimation actually does when we get to regression type problems. So our prior probabilities, here you can see that this is a little bit different, again, because there was a slight difference in the randomization. That's okay. So we have our prior probabilities here and here. It looks like I was not using a seed at this point. Frequencies in the training data, that's how we're generating those prior probabilities. Now let's look at one last example or one last data set that we might use for classification. This data set's kind of interesting. So this data set is the scheduling data set. This is information on 4,331 jobs in a high-performance computing environment. So high performance computing refers to using server-based computing to execute a task much faster than you might be able to on your home computers. So typically a high performance computing center, such as the one at the University of Nebraska-Lincoln down the road, works on a batch system. So jobs are submitted to the HPC. The HPC estimates how long they think the job will do and tries to allocate server time to complete as many jobs as possible in a reasonable amount of time. So we want to have a good balance between things we think will compute quickly, things that we think will take a long time to execute. So we have several input variables. We have the type of computation or the protocol. We have the compounds, so this refers to the number of data points for each job. The input fields, the number of characteristics that we're estimating. The iteration, so how long we'll let the computations run for. The number of other jobs pending in the queue. And then we have time, hour, and day. The classes are very fast, moderate, and long. So we'd like to optimize our performance and see if we can come up with some way to, based on these input variables, estimate how long the class will take, or the computation will take. So this data set comes from the Applied Predictive Modeling package in R. So I'll call the Applied Predictive Modeling library. We'll take a look at the scheduling data just to get an idea for what is involved. So protocol looks like it's a categorical input variable. Compounds is numerical, inputs fields is numerical, iterations numerical, number of pending jobs numerical, hour, day, and then class. Hour is in military time to the decimal point. So looking at this data, we might pick just two input variables to get an idea of how our classification might perform. So we've got compounds and input fields. Each point here is representing a different class. Looks like the very fast jobs are over here with relatively few compounds, maybe a lot of input fields. As we're increasing though, we're seeing jobs that are maybe fast, medium, and then jobs that take a long time to execute here in purple. We also have quite a bit of problem with skewness. We also have quite a lot of compounds at particular intervals. So at particular values, maybe 4,000 here. This looks like about 2,500. So in general, what we might be seeing are maybe jobs from the same lab, calculations on the same data, trying to address the same problem, things like that. One thing that can help us when we're fitting a machine learning algorithm is to rescale our data. So what I've done just in this plot is transform compounds and input fields to be on a log 10 scale. So what this does is break apart this clustering of values near the origin and lets us see where some of those distinctions might lie. Even though we're only looking at two of the input variables, and granted, these might not be the best classification variables to work with, there's still a ton of overlap from class to class. So this scheduling data problem might be more difficult in terms of implementing the estimation. The classes are much less distinguishable, so let's try a couple different approaches and see what works best. We're going to try two naive Bayes approaches. We'll talk about why logistic regression isn't really an option here. We'll try naive Bayes with the balanced training testing and with unbalanced training testing. Here I'm going to use that 80-20 split. So for the balanced training testing, we'll create our data partition. For the unbalanced training testing, we'll just use simple random sampling to select our rows. So we've got scheduling train balance, test balance, train unbalance, test unbalance. In order to know which is going to be best for the particular scenario we're looking at, there's no rule of thumb. Let's just try both and see what happens. So we'll do naive Bayes on the balanced training testing data. We'll use all of the input variables here, so we have 7 predictor variables, 4 classes. Again, how we know we're using all of the input variables is that we're just using a dot on the right-hand side of the formula equation. Our overall accuracy, there are some major gains going from assuming a normal distribution to using kernel density. Look how much the accuracy here is changing. Part of that has to do with the fact that there's no way that compounds, for example, follows a normal distribution, or input fields follows a normal distribution. So that kernel density method is going to do much better for us. Even still, we're not seeing significant gains when it comes to kappa. Looking at the predictions now on the testing data, so I'm going to predict, use that as my prediction. We'll look at our references from the testing data. We're not doing great. A lot of our actual very fast jobs we're predicting to be fast. So we're actually doing worse with misprediction here. We're predicting more wrong than we are right. Fast, we're predicting more wrong than we are right. Medium, we're really not doing great. And then long, we predicted none of those correctly. So our overall accuracy is about 49%, 95% confidence interval for the accuracy rate here. And then we can look overall at a class by class breakdown. So for that class L, we didn't predict any of them correctly. So our detection rate, for example, is 0. We're not doing well. If we use the unbalanced training testing data, let's see if we can get an improvement. Intuitively, think about what might happen. Here's our accuracy. Here's our kappa. Again, kernel density estimation is doing much better with the unbalanced training testing data. However, the accuracy has gone down slightly compared to when we had balanced samples. Again, the confusion matrix doesn't look great. Overall accuracy is a little bit worse than before with the unbalanced training testing. So if possible, it looks like the balanced split is doing a better job here compared to the unbalanced split. Both of the models are doing a pretty bad job with that fast class. We're not actually identifying any of them. And overall, naive Bayes doesn't really seem like it's working very well. So the question at this point becomes, is it because the data is too variable, or is it because of the method we selected? Maybe naive Bayes isn't the best approach. The answer is something that we'll find out next week. Last question to think about with this section, why can't we use logistic regression? Why isn't that an option to compare? Well, we have 4 classification tasks. And again, logistic regression only works well with 2 classes. So that's why at this point we have nothing to compare to. Next week, we'll talk about 2 more classifiers. At this point, you should head over to the Section 3 quiz, give that a shot, and get started on your homework for next week. Have a good weekend, and I will see you guys on Tuesday the 28th.